Okay, on to the second half. We are going to find the equation of a line that's tangent to this crazy thing at this particular point. So again, it's implicit. That's what this section's all about. We take the derivative of both sides. This is tedious on the test. I will not make them be this long, but it is really good practice to go through it, grind it out. It's just 3 times the product rule here. There that is. I've taken the 3 out just to make that really clear that anytime you have a constant times a derivative, you can just take that out, find the derivative of what's going on, and then multiply it by 3. We do have to be careful that this is then a product rule, and there's a plus there, so we just distribute the 3 in. The distributive of 2 is 0. Again, a little mini product rule. There it is. This times the derivative of that, 2y, y prime, plus that times the derivative of this with just a little bit of 1 that's dropped out. Derivative of sine is cosine. Don't change the inside, then there's the derivative of the inside. We've gone derivative of x is 1, and then we've used a little chain rule there again. So just do that very carefully. Now I have to distribute this in. This is what we've had a hard time doing in class, just making sure that you see that this is all one thing multiplied by something with a minus sign there. So you must distribute that in. Times 1 is easy, then times this is just going to give you a big awkward mess. But there that is right down there. You'll see that. There's that second part right there, and there it is right there. Okay? Then I've got to identify where my y primes are. There's one, and there's one. Right? So there are 3 different y primes. Move them all over to one side. I've chosen to move them to the left. That one stays there. This one moves over. It's minus. This minus cosine moves over. It's plus. There are the y primes right there. Again, we just are trying to group them and then factor them out. Here's everything else. The y squared doesn't change. This 6xy moves over and is negative, and this does just stay there on that right hand side. Okay, so once I've factored this y prime out, there it all is. On the denominator, when I divide, here is this unchanged in the numerator. Then I'm going to take my point, right, and I'm going to substitute it in right here. So in for the y goes 1, in for the x goes 1. It's a little bit easier. Everything is a 1. And I've gone through carefully, subbed it in. The cosine of 0 is 1. 6 times 1 times 1 is 6. So it becomes 1 plus 1 is 2. Minus 6 is negative 4. Then it becomes 3 minus 2 is 1. Plus the cosine of 0 is 1, e to the 0 is 1. So it becomes 1 plus 1, 2. So this equals then minus 2. That's my slope of that tangent line. So then I just have to plug it into point slope form and simplify it if you want. It does not matter. All right? So that's 3. So now for the logarithmic differentiation, we have got this thing, which we can do much more simply if we simply take the logarithm of both sides. All right? So I write it as y equals, because we don't sort of take the ln of a function notation type thing like that. So I make the f of x into a y, then I take the log of both sides, and I'm just really making it clear that this is multiplication. So when I break it apart using my laws of logarithms, I get ln of y, then that 1/3, all the exponents come out front, and that's what makes it so much easier. Well, when this comes out front, and I'm taking the log of e to something, poof, the log of e, the natural log of e is 1, and so you'll see there's no log there. It's just turned into 1. Then I bring this out front, so it's 10 ln of that x to the 5th minus 2. Well, now I differentiate. Okay, I do differentiate implicitly, and it gets simpler because we just get 1/3 times the derivative of ln, which is 1 over x. This is just power rule. Again, we take the derivative of the ln. This just goes in the bottom times the derivative of the inside up on the top. And that's all times 10. So it simplifies fairly quickly. Nice little problem here. And you can write it like this. And then it's going to be times. To get rid of that 1 over y, we multiply both sides by y, or you can just write f of x. If you want to recopy the whole thing, it's going to be the 3rd root of x, e x to the 7, and then times x to the 5th minus 2 to the 10th. Okay, so you could write that all down also, but not necessary to waste that time. That gives us time to move on to 5. Linear approximation. All right, we're given this decimal, and think about it. If you're going to multiply this times itself 10 times, you could be doing that for days, weeks, years. Estimating it, you might not have any clue, but by using calculus, we can get a very, very close estimate. Fact is that it's got to be close to 2. All right. Well, you can multiply 2 times itself 10 times in about 30 seconds. It gives you 1024. We're imagining that we are doing this without a calculator. You can, of course, use your calculator to do that sort of thing. If you really want to do it without a calculator, you can. But we're showing the technique that's powerful for finding these estimates. All right. So then, once you've found this 2 to the 10th, we're going to take the function, the sort of parent function of this is something to the 10th power. It just happens to be this decimal. When we take the derivative of that x to the 10th, we get 10x to the 9th. That is the equation for the derivative. And then I plug in 2 into my x. So f prime of 2. This is going to tell me the slope of the tangent line at this very, very close to this instant point is going to be 2 to the 9th, which is 512 times 10. So the slope is 5,120. So that's a very, very steep slope. For every 1 unit it goes over, it goes up 5,120. We're just going a little ways over. So how far are we over? We're subtracting from 2. So we're just a little bit before the 2. That's why it's negative. So we're going sort of backwards from the slope. If this was a function that was curving up steeply, we're finding a point here and we're saying, oh, there's the slope that's really steep, and we're actually looking for a point that's right there. And so we're going back and we're just saying sort of how far down are we over and how far are we going to the left. Well, we just multiply 5,120 times 0.013. Again, I've done it without a calculator here. You do not absolutely have to use a calculator, but you're invited to if you want. It is 66.56. So when I take 1024 and subtract 66.56, again, I've done this old school method just to show you don't absolutely have to have a calculator. You get this as your estimate. All right? Compare that to what the calculator says, and we are very, very close indeed. Okay? Just slightly less than 1 unit away in 1,000. So not a bad estimate. All right? Good luck with that. Hope that helped. Here's a quick scan of all the answers, just so you can check your work. In case I missed anything, some of it was chopped off.